everybody, welcome to this edition of the live stream. This is IoT Design Week, day 5, and today we're going to be talking about low power sensor networks. My name is Mark McComb. This is your opportunity, as we're broadcasting live, to interact with our panel of guests here on topics related to low power sensor networks. So I've got Patrick Kennedy from Microchip, and I've got Mr. Tim Reskers from Codo Technology, and we'll get to know these gentlemen in a minute. First thing, what I want to do is just kind of recap what we talked about this week on IoT Design Week. So if I can get my list, because I got a bad memory. So we talked about on Monday home automation. We had some cool demos with that. AI and machine learning. We also talked about security, which is very important when you're dealing with IoT networks. And then yesterday we went through some maker-focused topics. So today, hopefully, we can expand your knowledge on this and talk about low power as it relates to sensor networks. In the meantime, let's go to the booth and talk to Edwin and Ross and see how you can interact with us and what kind of prizes we're giving away today and so on.
Yeah, that's right, Mark. Hello to everyone. Again, if you have questions, get them ready. We'll be monitoring the YouTube chat, Facebook, and LinkedIn, and we'll bring those questions to the guys up in the desk. We also have 2 prizes to give out. We have our Sensors Expo ticket and Embedded Technologies Expo tickets. We'll be sending out a survey towards the end, and you can fill that out, and then we'll pick a winner. And again, those, if you can't make that, you'll have other options to win other prizes. We also have a discount code for the event, or the expo event. We'll put that discount code towards the end on the chat. But yeah, there's been some exciting week this week with a lot of IoT. So how's it going, Ross? How's it been so far for you?
Pretty good. I really enjoyed the Maker event yesterday, but I think my favorite one is going to be today's low power.
Yeah, I'm excited to hear what Tim has to talk about today. But yeah, well, so everybody get your questions ready. We'll be monitoring the chat, and I'll send it back to Mark. Go ahead.
Cool, thanks guys. So again, if there's something that we're not covering on here that you want to talk about, you know, that chat window's there, and if we don't cover it on the live stream, as Edwin mentioned, there are some engineers online who are answering questions that way too. So without further ado, let's get to know our guests. First we have Tim Resker from Codo Technology. Yeah. Tim, tell us about yourself and Codo.
Yeah, sure. So my name is Tim Resker. I'm the Business Development Manager for Codo Technology. And Codo is a leader in signal switching and in magnetic sensing. And I basically work with customers that are designing systems where they're trying to solve a problem with magnetic sensing.
Very cool. So very relevant to today if Tim works with customers on a regular basis to discuss this very topic. So great, nice to have you, Tim.
Thanks for having me.
Patrick, I've worked with Patrick for a couple of years now. Patrick Kennedy is with our technical marketing group. Patrick, can you talk a little bit about what you do here at Microchip?
Yeah, so I work in our 8-bit microcontroller business unit, and basically my role involves focusing on ease of use, rapid prototyping, and basically making all kinds of collateral and training materials so that our products are as easy to use and design in and with as possible. So that includes things like video tutorials, code examples, you name it, we make.
And you just did a video on low power, did you not?
Yeah, I did. I briefly went over just how to, basically how you can put these devices into low power modes that one of our app scripts actually came up with.
Oh, very nice.
A more entailed application, but I tried to boil it down to the basics.
Yeah, and we're going to talk about some of these low power modes, and these are modes that you want to keep your device in for, you know, especially when you're considering battery applications, or even if you're looking at things like energy harvesting and that, and we'll talk a little bit more about that. But before we do, let's kind of put everything into perspective here. And guys, if you can go to my computer screen, what I'll do is I'll give you an overview of kind of what we're talking. So in the world of IoT, Internet of Things, you know, essentially if we boil everything down, we're dealing with these things, and these things could be anything from a speaker that is receiving information over the web, or a microphone that's inputting information over the web, or you know, anything, robotics, a coffee maker, lighting, temperature, security, all that kind of stuff. And when we're going to kind of try and discuss different ways to connect to the internet, there's some options. Like we have some tools that allow you to direct a thing, which is probably going to be made up of a microcontroller of some sort and some sensors, and we're going to connect that to the internet. And there's platforms that we have that will connect directly to the internet, either wirelessly or directly through a wire connection. But we also have the option to do things with an intermediary device, so a gateway device, in which could be your cell phone or another MCU, a higher performance MCU that maybe acts as an arbitrator and then takes all this information from all these different sensors located around wherever your application environment is, and then transmit and deal with the cloud. So if you're dealing with things like a web service, that kind of thing, then maybe you have a device that runs very fast and is able to, process that data very quickly, and then you can keep your sensors, your nodes, if you will, in a lower power state and only use that gateway device as something to stay on all the time and process this information. And if we kind of take a little closer look at the thing, which we're going to focus on today, you can see that there's a number of requirements that you probably are familiar with. Some you may not be, and some you may guess that aren't on this slide, but you can see that we're going to talk about the size of the application, responsiveness, security is a big one, cost, robustness, are you dealing in harsh environments, sensor interface, which we'll talk more about today, and then of course the low power aspect. So having said all that, so Patrick, I'm going to pose you a question. What does low power mean?
Yes, that's a really good question, actually. And I think that's something that every designer, anyone who's trying to make some sort of product or improvement will have to ask themselves inevitably, right? Because for some applications, you're looking at nanoamps as low power to you, versus other applications it might be something more in the milliamps or even higher. A really good example of this might be, for example, if you have a remote sensor node when you're monitoring, let's just say, wildlife traffic in a given area, right? That's very remote, probably a very small form factor, and you probably are not going to want to have to change that battery very often, if at all. Maybe it's running off of a solar panel or some other kind of trickle charge. In that case, you're probably going to want, something that can sleep for a while, really low nanoamps.
Right.
Versus you have, on the other end, something more like what I would call like these e-scooters that you see in a lot of cities, right? Where they have full-on motor control. And in that case, shaving off a few nanoamps for those applications, it really doesn't make a big difference in those larger systems. But there's still those can still be considered nodes, right? Because they connect to a network and provide information and services that we use every day.
And it's kind of a balancing act, right? As well, like you put things in perspective. I mean, we sell everything from 8-bit to 32-bit to MPUs to analog devices and so on. But it's just, and the reason we do that is because there's all sorts of different applications. There's all sorts of different requirements. So, low power is a subjective term. Now, if we're dealing with low power, there's a couple of variations of this. When you're dealing with microcontrollers especially, we have dynamic and static power. And this may come up during our conversation. Can you kind of explain what those two aspects of the application are?
Yeah, sure. So basically what it can boil down to is static power is basically the amount of power that your system will consume when code is not being run. That's usually through things like transistor leakage or passive components or what have you. Whereas dynamic power consumption is more so when code is being run, and that's when you actually have the clock actually switching the transistors, on and off, which is really important, kind of in the case that I just mentioned with, comparing something that's super remote where nanoamps is what you want. In that case, you're going to be sleeping a lot of the time, and when you're sleeping, you're putting the CPU to sleep, and not using it at all.
Right.
So in that case, your focus there will be, I need to have a very low static power consumption. If I come out of sleep, let's say once every day, once every several days, it's okay if that's a little bit higher, because overall I know that my static power consumption is in the nanoamp range, for example. Versus, as I mentioned before, in the case of some kind of e-scooter or something like that, where it's a much larger system, and you're expecting, okay, I'm going to be constantly running code because my application demands it. In that case, you'll have to focus more on lowering your dynamic power consumption.
Right.
So it's really just a trade-off of what you're trying to do. What is
And then to execute maybe some line of code very quickly and then get back into that lower power.
Exactly, exactly.
So Tim, we're talking about these low power modes. In some instances, the reason for them is to extend the life of a battery in an application. So you want to keep that application in low power mode as much as possible. You know, you can hear numbers like in the upper 90 percentiles to keep that device in low power mode. Can you talk about how designers have traditionally met that challenge?
Sure. So, you know, obviously, for IoT devices, you want to keep them in a low power mode. And then the challenge becomes what mechanism to use to bring it out of the low power mode to essentially to turn it on.
Right.
And, you know, traditionally, designers have used different methods for doing that. They've used on-off switches. They've used battery tabs, pull a battery tab. But what they've trended towards are, in many cases, is using magnetic sensors.
Okay.
Because magnetic sensing is contactless, it's non-mechanical, doesn't really require a switch. So if you've got a hermetically sealed IoT device that's out in the environment, or it's being worn by somebody who's taking showers and swimming, you can employ a magnetic sensor to turn the device on or wake it up without any mechanical contacts.
Right, and that's, you know, we're going to talk a little bit about robustness, and that's definitely a part of it.
Absolutely.
Harsh environment that could be moist or whatever. So Patrick, can you expand a little bit on some of the low power technologies that you would find with a microcontroller? So Tim talked a little bit about mechanisms to exit these lower power modes. So you can use a sensor like this, and we'll show Tim's board there,
yeah.
and show how we can get different signals out. But can you talk a little bit about how we would implement low power on a microcontroller?
Yeah, sure. So there's a few different modes that we have on both PIC and AVR, and even some of our higher-end SAM devices, as you mentioned. Really what it comes down to is, I like to boil it down to something called idle mode, which is one of our low power modes. Sleep mode, or power down mode is what it's called for AVRs, but it's essentially the same thing. And then doze mode.
Okay.
So basically doze and idle mode are similar, where you're basically going to, you're still running your clock, but you're not actually allowing the CPU to run. In the case of idle, it's just completely idle. It's not really doing anything, but that clock source can still be used by other peripherals, which can lower power consumption pretty substantially. Or you can have more of a doze mode, where the microcontroller kind of executes code, but every so often,
Right.
every so many instructions, right?
Okay.
But all of those extra instruction cycles are still left to the other peripherals. And then finally, you have something like sleep mode, or even on some devices, you have deep sleep mode.
Yeah.
And in that case, you're completely shutting off the system clock. And there's still actually quite a few peripherals that you can still use, even when that's shut off, or even through an external clock source, which allows you to do things like taking sensor readings, detecting things on a pin, interrupt on changes, and even actually doing some internal data movement, which is pretty useful, right? If you, for example, with some of the analog to digital converters on our chips, you can start accumulating samples and then wait until you say have 32 samples, and then you can decide to store that then.
And this is in the lowest power sleep mode on some of the devices,
Yes,
right?
yes. The thing is that you have to be kind of careful of sometimes, especially when you go into things like deep sleep mode, especially, is that requires a certain amount of extra power to wake back up, and there's also a bit of latency associated with that as well, right? Similar to how when you get out of bed in the morning, most people don't just spring up and go straight to work. You kind of have to get up, turn off your alarm clock, go back to sleep for another 5 minutes, and then
Right. Or half an hour.
Yeah, exactly.
Okay. But again, it's a balancing act for your application. I mean, there's a lot of times where we have customers that have libraries that they need to reproduce, and this is just something you can't do in hardware. In this instance, you want to get a device that can run fairly fast, be able to execute code, and there's a number of things to keep in mind there. There's oscillator speeds, but there's also like the type of architecture you're dealing with. Some of our devices take 4 instruction clocks to execute a line of code. Some of them take 1. So if you look at our 32-bit devices, you're dealing with a lot faster. These are very optimized cores for running software. So it's again, it's all a balancing act. There's not a one fit product for all applications. Sometimes you're going to need an 8-bit. Sometimes you're going to need a 32-bit, and that's the whole idea here. So Tim, we talked a little bit about the microcontrollers, but can you tell us a little bit more about solid-state magnetic sensors?
Sure. So, as I said, magnetic sensing, for quite a long time has been a popular means for doing a lot of different things. And one of them, particularly with IoT devices and battery-operated IoT devices, is this wake-up or power-on function. So using a magnet, an external magnet with a sensor in your device to essentially signal a microcontroller in most cases to wake up.
Okay.
To say, okay, now the product needs to be powered on, and we're going to use it.
Okay. And you have can you show us your demo
Sure,
board there?
absolutely.
'Cause-
So here's a demo board that we developed that really illustrates what we're talking about here. So we've got 5 of our sensors on here. These 4 are digital sensors. This one is an analog sensor. But this one in particular right here, its output is connected to a circuit that controls power on and power off to this particular demo board. I mean, think of this demo board as an IoT device, okay?
Right.
And the way we illustrate that is we've got this little carrying case here, and as you'll notice, inside this carrying case, we have a little magnet in there, okay? So think of this case as what the IoT device gets shipped from in the factory, okay? So when it's in the case, okay, and the sensor senses the magnet, that's connected to a circuit that powers the device down or puts it into a sleep state, okay? So it's sitting on the shelf, it's, whatever, and then it's ready to be used or deployed. Somebody takes it out of the case or the package, moves it away from the magnet, and it turns on,
Right.
okay?
And so this is, obviously, if this is something that's sitting on the shelf, the current draw on these devices is going to have to be fairly low.
Of course, very low, right?
Yeah, so
that
what's-
would defeat the purpose.
Exactly.
So these sensors are based on a technology called tunneling magnetoresistive technology. We call it TMR for short.
Okay.
Okay. And it's a technology that's been around for some years, but only in the last 5 years has it been commercialized. Now we have these sensors that we sell, and the average current drain on these is as low as 100 nanoamp.
Wow.
Yeah.
Okay.
And that's extremely attractive to
Yeah.
to designers that are developing battery-operated devices that want to use a magnetic sensor for some type of function, whether it's whether it's a turn-on function like we just discussed, or even a proximity sensing. So let's say you've got some product that has a mechanical component to it.
Yeah.
It could be something as simple as it's got a lid or a door, and you want to be able to detect whether that's open or closed. Okay, so you've got your magnet on the moving component, you've got your sensor on the fixed component, and you can then do proximity detection.
Very cool. So this is for such a small little board, it's got some really cool little demos on there. Can you walk through some of the other ones?
Absolutely. So, both of these sensors are fairly similar. This one happens to be a 30 Gauss sensor, which means when it sees 30 Gauss of field at the sensor, it changes its output.
Okay.
So with this magnet, 30 Gauss is that distance.
Okay.
Okay. And then as we pull it out, it stays off and then it turns
look at
back
that.
on. So there's some hysteresis.
Yeah,
right?
yeah.
Okay. All of these digital sensors have some hysteresis. So that's 30 Gauss. This one is 9 Gauss. Okay. So obviously 9 Gauss means the sensor needs less magnetic field to operate it, which logically means it will operate
Oh, nice.
from a further distance with the same magnet.
Okay.
Okay. Another benefit of TMR technology is it's extremely sensitive, which means you don't need as much magnetic field to operate it, which means you can often use a smaller, cheaper magnet. And you know, magnets are part of the BOM cost, so everybody's looking to reduce their BOM costs.
Right.
Okay. Both of these sensors are omnipolar sensors. They operate the same way, whether it's a North Pole or a South Pole. But we do have sensors such as this one up here. This is what we call a dual unipolar sensor, okay? And it has two outputs, one for each pole, okay? And there are applications where customers might want to be able to detect what pole it's seeing, okay? This sensor up here is a bipolar latching sensor, okay? It will turn on and stay latched on with the North Pole, and then with a South Pole, it will turn off and stay latched off.
cool.
Good application for that, common, is you've got some type of a rotating shaft. You put a ring magnet on it with diametrically opposed poles, and as I rotate this shaft, you can see, get my hand out of the way, you can see that the sensor is turning off and on, hard to see, with every rotation.
That's cool.
So it's a good rotation counting mechanism.
So I
Okay.
could use that in a motor control application, maybe?
Not so much motor control, but if you've got some rotating element like
Oh, sure.
a wheel or something like
Okay.
that, or a shaft, is common. And then this one down here is really exciting. This is our analog sensor. Okay, so it provides a voltage output that's proportional to field strength.
Okay.
Okay, so we've got a magnet. All right. So without a magnetic field, the output is half the supply voltage.
Okay.
Okay. As we apply a South Pole, the voltage goes from half the supply voltage to full supply voltage.
That is cool.
proportionally, linearly. Okay. And then we apply the North Pole, and it goes from half to zero. Okay. So with a given magnet, you can then correlate to distance. So this is a sensor that will allow you to measure distance
Okay.
where the magnet is. So level sensing applications, liquid level sensing applications with magnetic floats that are going up and down based on the volume of fluid in the reservoir.
Such a simple thing, but you can think of so many different ways to use them. It's
absolutely,
how cool
yeah,
is that?
yeah.
I think we have a question in the booth.
Yeah. Someone on the YouTube chat has how much power consumptions do the TMR sensors consume?
Sure. So the power consumption is as low as 100 nanoamp. Another thing I didn't mention, and we might get into it later, but the digital sensors have a sensing frequency. And for most applications, you don't need a high sensing frequency. So maybe 10 hertz, 2 hertz. And in that case, the power consumption is as low as 100 nanoamp or 200 nanoamp range. If you go with a higher sensing frequency, maybe because you're trying to detect a rotating magnet, and you don't want to miss the magnet when it comes around, you might need a slightly higher.
Yeah.
But it doesn't increase the power consumption that much. I mean, they're really extremely low power.
And it's like with our devices too. It's like there's always a balance between what do you need to do versus low power versus performance, that kind of thing. So there's more questions from the booth.
That's correct. So one question from Armstrong Subero is the hysteresis integrated on the chip, or is it software based?
Good question. So the device is not programmable. So it comes with set parameters. So the hysteresis would be set. So for example, I mentioned this sensor right here is a 9 Gauss sensor. Okay, it's 9 Gauss operate, 5 Gauss release.
Okay.
So that 4 Gauss is the hysteresis, and that is fixed. But we offer products and variants that have different sensitivity levels, different sensing frequencies, different hysteresis.
Okay. Is there more from the booth? Or?
Yes. Is there a minimum or a maximum speed of the magnet passing the sensor to produce a clean output pulse?
Yeah. So again, that gets back to sensing frequency. So if you've got let's say you've got a rotating magnet, you need, depending upon the RPM of that magnet, okay, you need to choose a sensing frequency that's going to be able to catch it. So it's like sort of like a Nyquist formula type of thing.
Yeah,
we
yeah.
need to figure out. We help customers figure that out. so that it's ensured that every time that magnet comes around that the sensor is going to catch it.
Okay. Anything else, Ross?
That's it for now.
That's it?
I have a question, right? Sorry.
okay.
Yeah. There's one question. What's the maximum sensing frequency?
Okay, good. So maximum sensing frequency is 10K hertz.
10K hertz?
Yeah.
Okay.
Okay.
And there's one more. Sorry. What is the specific life of the sensor?
Yeah. So again, you know, it's a solid state device. So
Yeah.
it's it'll last forever. So unlike, for example, you know, traditionally, for a lot of these functions, people have used reed switches, and I don't know if the audience is familiar with the reed switch, but it's an electromechanical device. It's two reeds that when you apply a magnetic field, they get pulled together. So electromechanical devices, mechanical devices, by their nature,
This is where
are they're going to wear out. They're going to fail. And what we see is everybody's looking to move away from anything that's mechanical,
Right.
whether it's an on-off switch or a reed switch or whatever. And that's the beauty of this. There's no moving components. So to answer the question, you know, the reliability and the lifetime of these sensors is limitless.
Yeah.
Okay, we have another one as well.
Okay.
What is the latency between the magnetic field being present and the sensor asserting a high or low voltage?
Yeah, good question. It's I don't know the answer to that. It's extremely low. I mean, it's pretty much instantaneous.
Yeah.
And for and for most applications, like pulling it out of the box, it's certainly fast enough for that.
Yeah,
But
yeah.
it's very low latency. The response time.
Okay.
The output response time.
Thanks,
That's it.
guys.
Yep. Thank
Okay,
you.
cool.
Yep.
Hey, great questions. Thanks, everyone.
Yeah.
Please keep them coming. So Patrick, we're seeing on this board a couple of different signals that are coming out. So we're having like digital signals from some of the sensors, and in the case of this sensor over here, we have an analog signal. So can you talk about some considerations when you're using a microcontroller that you would, dealing with different signals like this, like what kind of features are on these devices, that kind of thing?
Yeah, sure. So just in terms of the differences even between dealing with analog and digital signals, analog, usually you'll want to make use of an on-chip analog to digital converter, as I mentioned, since you can function in sleep when you use that, and you even have some extra additional features in a lot of our newer devices where you can do things like filtering, accumulation that will really help you cut down on power, and you can actually get a cleaner signal if you need if your application
That's what I was
requires
going to
that.
say. If you put it's a good idea if you're doing an analog to digital conversion to put the device into sleep because you have noisy clock sources, all that kind of thing going on.
Yeah, exactly.
Okay.
And then if you happen to basically pick up a value that is above, let's say, a predefined threshold or window or what have you, usually that can serve as a wake-up source for the device in any case.
Right.
Now, in terms of digital signals, it gets a little bit more, I don't want to say complicated because it's not the right way to say it, but one of the biggest issues that people run into with digital signals is more or less a lot of sensors nowadays you have to hook up on like an I2C bus, right?
Right.
Which if you're adding a ton of sensors to your application can be useful until you start getting really high up. Then you have things like bus collisions and arbitration that you have to deal with.
Right.
And one thing I think that's really neat about Goto's sensors is that since their digital sensors are, like you mentioned, they're not software programmable, they're fixed. All they really provide is just a high or a low based on the sensing of the field, which makes it really simple. I mean, a simple I2C transaction, is a few bytes at least to have to handle and do all of the acknowledgement checking and whatnot. Versus this kind of provides a very easy escape from that, for lack of a better term.
And we talked a bit about the robustness on these magnetic sensors going into like harsher environments. And when you're dealing with serial communications, there's sometimes you're getting a little bit of chatter on the line. And can you talk a little bit about how some of our devices overcome that?
Yeah, sure. So, I mean, one of the biggest things is going to be basically your level of noise immunity, right?
Yeah.
So, if all of if my highs and lows, if they have a larger distance between the two, you're basically going to have a bigger cushion, for lack of a better term, where you can kind of filter out the noise, right? So, the difference, for example, between if my low is 0 to 6 volts and my high is 2.3 to 3 volts, right? If I have the same system, but my low is 0 to 1 volts and my high is 4 to 5 volts,
Yeah.
that is a much more robust system in terms of environmental conditions.
Well, if you're dealing in an area like where there's a lot of machines running, stuff like that.
Yeah, or even as Tim mentioned, somewhere where there's going to be liquids present. Like you mentioned, you have applications in like level sensing. And I know that for magnetic sensors, especially, I guess what I think of in terms of with these devices is being able to hermetically seal is really valuable from a manufacturing standpoint. It's really hard to actually get all of your gasket fittings right if you have a more mechanical based system where you use like a button or something like that in your around fluids, and that kind of is another environmental consideration that I think is
for
important.
sure. So I think we have a question from the booth.
Yes. So, are there any versions that are ready to use for harsh environments, such as, for example, an oil platform near the sea, or coping with vibration?
So that's for Tim. I
Okay,
guess?
yep.
Yeah.
So, yeah, I mean, typically the way customers solve that is they hermetically seal everything, right? It's, IP, perhaps to IP69 or whatever. The electronics are just sealed up. The
Yeah.
magnetic's sealed up, and generally that keeps it safe from the environment.
Okay.
Okay. And another one, what is the advantage over Hall effect sensors?
Yeah, so it's good, great question. So Hall effect sensors is another type of magnetic sensing technology. It's been around for decades.
Forever, yeah.
Hall effect sensors functionally are very similar to TMR magnetic sensors. The big difference between TMR and Hall effect sensors, or two big differences, is one is Hall effect sensors consume a lot more power. So again, for battery operated applications, TMR is a superior technology.
Okay.
The other advantage is higher sensitivity. So you need less magnetic field to operate a TMR sensor than you do a Hall sensor, which means smaller magnets or being able to detect a magnet from a further distance.
Okay.
Cool. All right, thanks, guys.
Thank you,
Thank you.
Tim. Appreciate it. Now we talked a little bit about application size. Now, Patrick, can you talk a little bit about so one of the things, this is a little bit of a deviation. So we have low power sensors that we want to keep probably far away on a battery. But we also want to concentrate on the size of the application too. Tim, you talked a little bit about the size of these sensors. Like how small can they get?
Sure. So they can get very small. So we offer our sensors in two different packages. Either a SOT23, which are these, common SOT23 package, but also an LGA4, which is extremely small. It's 1.4 by 1.4 millimeters.
Okay, and we've Microchip. We have taken a philosophy to, especially with our lower end devices, to integrate a lot of components on there. Can you talk a little bit more about how we try and keep the application space small, the real estate required?
Yeah, definitely. So I mean, a lot of our like you mentioned, our lower end microcontrollers have more what we would call like integrated analog components. Like I mentioned, an analog to digital converter with some computational features, and that's just one of them. We have other things like op amps, like pretty high resolution PWMs, I2C and SPI, and other serial comm peripherals that can more or less operate independent of the core or with very little intervention from the CPU. And that, like you mentioned, brings along some real estate savings on your board. So you can really save a lot of space, which at the end of the day saves time, and in a lot of cases it can save power, right? Because you have less traces that you're going to have some kind of loss over.
And that's kind of a good point too, because if you have, and not necessarily a new design, maybe you have an existing design and you come across some new technology, and in our case, maybe a new feature on a microcontroller, that is maybe a logical next progression for a customer to go to. So, this new product has a DMA on it. And the customer wants to take advantage of this, but they don't want to redesign their whole application. Can you talk a little bit about how we kind of reduce that or minimize that redesign?
Yeah, definitely. So, I mean, migration is always a touchy subject for people because, as you mentioned, they don't want to have to redesign everything from scratch. So one thing that we offer a lot of the time is most of our devices, especially the PIC devices, have peripheral pin select and mapping. So basically that means you can just map your peripherals to whichever pins you need, and that's on most devices. So that means that if you want to get set up with a new device, you don't have to worry as much about the pinout, right? And checking the data sheet to see, okay, like which pins do these go to? How much am I going to have to change my my PCB design? I mean, inevitably you might have to change it a little bit, but it really kind of saves time doing that. And then even with the configurable logic cells or configurable logic on both PIC and AVR devices, you can almost functions as a little bit of basically glue logic, where you can do something similar, where you can map peripherals to peripherals or peripherals to pins to other pins that even might not be mappable through the peripheral pin select. So it gives you a lot of flexibility as a designer to, like you said, add features as you need, basically.
And Tim talked a little bit about waking devices up from sleep using the sensor. And one thing that I think is really cool with the configurable logic that are on some of these devices is the fact that because in certain modes, if you don't need to use a clock for the peripheral, the device can actually stay in a low power sleep mode, and say you have one of Koto's sensors connected to one input, which is generating an interrupt on change, but you also have maybe a analog signal connected to a comparator and maybe another one of Koto's sensors that maybe when it hits a certain voltage level, you want to wake up the device. You can actually take both those signals and then run them into a configurable logic cell, for example, which is triggered to wake the device when it's asleep. So that's multiple conditions to wake up a device. What did you have to do before? You had to maybe use one of the signals as a trigger to wake the device up, and then the CPU powered up and went in and checked for these other conditions that existed, and then the device, if the both conditions weren't true, then the device goes back to sleep, and you just wasted power waking up, going back and checking all that. Whereas if you were to use the configurable logic cell and the combinational logic, that actually can wake up the device when those two conditions are true. So a nice power saving feature there. So that's kind of, that's a static power example. We talked a little bit about dynamic power. And I mentioned at the beginning of the cast here about instruction set architecture, frequency versus power consumption. Can you expand a little bit on that?
Yeah, sure, a little bit. It starts to get into a bit of a dry subject. You get too far into the computer architecture side of things. But yeah, basically, for dynamic power consumption, like those are going to be applications, like I said, where you kind of know off the bat, like, okay, like there's no way around this. Like I do need to run a lot of code. Maybe you're doing some kind of really heavy signal processing. Maybe you're doing a lot of operations on floating point values. Maybe you're doing some kind of really heavy protocol where you're going to be connecting, very very frequently. And in that case, it's going to matter a lot, as you said before, to use a higher end device like one of the SAM devices or the PIC32s, because they can execute those instructions much more efficiently.
Right.
So yeah, I mean that definitely plays a big role. I think there's always as well a big trade-off between doing that versus trying to do something in hardware as well.
Yeah.
And it really just depends on the application.
Right.
It's all about throughput, latency, and power consumption because you're giving up something somewhere, right?
And the nice thing is that, you know, we have products that have 2 cores on it. You can maybe go down to an 8-bit device that has a DMA and maybe some of these other peripherals that can operate independent of the core. I mean, like I said, part of the strategy with 8, 16, even 32-bit devices is to integrate as much into hardware as possible so that you're actually kind of almost having a second core on the device because the hardware can now take and handle some tasks in the background while the CPU maybe does something else or goes into a lower power mode. Interesting. Okay, so we talked a little bit about electrical specs. Just as a quick aside, if we can go to my computer screen, I want to show you guys a couple of things. The first thing is we talked about the peripheral pin select on our devices, and what I do here is I have a Q10 device, I believe, open right now. Actually, no, it's a PIC16F18446. Regardless, this device has peripheral pin select capabilities. What we did, if you go to the data sheet on this guy, and you can click that right from MPLAB X, which I'm using here, you can actually go to the product homepage and you can open up a data sheet here and open up the data sheet. And you'll see here, as soon as it opens, probably should have had this open ahead of time, but that's my bad. But if you open up on the side here, you can come down here and take a look at the peripheral pin select module. And if you go into the data sheet, you'll see that there's lots of nice tables for you to refer to. So if you're doing what they call bare metal code or writing in C or assembly, you're going to need to understand these registers and what they mean. If you don't need to go into that much depth, if you come into the MPLAB code configurator, which I have open here, you can literally come in and just click on one of these pins in the pin manager here, and now you've assigned a signal to that pin. And you can see here, for example, the UART, I can actually run a transmit on multiple pins at the same time. You'll get a warning here if there's any conflicts, but essentially what it's doing is it's simplifying things. And you can see right now I'm using this pin as both an input pin, and I'm also using it as a UART transmit pin. Now the other aspect I wanted to talk about here with regards to the data sheet was that, you know, this may seem like very, you know, common knowledge, but you know, some people still don't know where electrical specs or things of that nature are. And if you go down to the electrical specs section, which is usually at the back of our data sheets anyways, you'll see all sorts of parameters to keep in mind. So how much current you can actually supply to the device, minimum currents, minimum voltage levels in order to achieve frequencies. So, you know, as you do faster operation on devices, you're going to need to burn a little more current at times, and this is detailed here. So the whole goal here is to give you the information you need to balance power versus performance. Okay, so let's move on. So Tim, when you're designing with magnetic sensors, can you give some design tips or some parameters that you need to be aware of whenever you're building applications using them?
Absolutely. Yeah. So there are some very common things that designers need to be aware of, and one of them is the axis of sensitivity of the sensor. So for these TMR sensors, and you'll notice when I was doing the demo, I was bringing the magnet in on this axis. Okay. And the reason I was doing that is because that's the way that the sensor is designed. That is the most sensitive axis. So you need to orient the sensor in the proper orientation,
Okay.
with regards to where the magnet's coming from. That's one thing. And then another parameter is what size type magnet. Okay. Obviously, what most people want to do is they want to use the smallest, cheapest magnet possible to meet the the parameters of their application activation distance.
Okay. Now with this, we have a question in the booth we'll go to in a sec. But I just out of curiosity for myself, can you use that as kind of like a cheap and dirty kind of positioning type of?
Oh, yeah, absolutely.
sensor?
Yep. You know, again, a good example of that is, you know, liquid level sensing. So where you've got a reservoir of fluid with a magnetic float, and then you've got sensors that are you know up and down,
down,
a ladder of sensors, and as that float moves with the liquid level, it activates the sensors, and that gives you positioning of the float, and hence how much fluid you have in the reservoir. And you can do that with either you know, digital sensors, or do it with our
With the analog one, yeah.
with our analog sensor. And the analog sensor, the sensitivity of it is such that you can get resolution close to 1 millimeter, which is pretty good.
That's awesome. So guys in the booth, question?
So we have a question regarding the angle of approach of the magnet to the sensor. What happens when the north and south poles are approaching the sensor pretty much together? What's the behavior of the sensor?
So it depends on the sensor. So you know, we've got omnipolar sensors. So they basically operate the same way with either pole. Okay. If you run the magnet like this, okay, you get a little bit of a, you know, a little bit of a blip in there.
Yeah.
But generally, our customers are, and this is how we help them with this to orient the pole in the proper way.
Okay.
And with an omnipolar sensor, one of the benefits is during the manufacturing process, you don't have to worry about which pole is facing it. The magnet doesn't have to be marked.
Okay.
Florin, one of our YouTube viewers, asks, do you have a sensitive enough sensor to build a wide-range Gauss meter?
Typically not. I think that's generally something that's done with more of a magnetometer type product. But you could certainly do a cheap and dirty Gauss meter using our analog sensor. Yeah.
Okay.
Depends on what level of accuracy and resolution you need.
Okay.
Cool. Thanks, guys.
Yeah,
Okay.
just one more. Someone was asking how could they get their, is that kit available to purchase, or how could they?
It is. These are, not only is the kit available, but our sensors are available from distributors like DigiKey, Newark, Mauser, or distributors of our products. But you can buy this demo board on DigiKey. They are
Okay.
available.
Great, thank you guys.
So that's kind of a good segue into just services that Kodo provides to help their customers get up and running. So if you have questions like this,
Sure.
what would a customer do?
Well, they come to us, and we talk about their application and what their needs are, and we talk about what type of sensor that will probably solve the problem for them. And then we've got application engineers that are experts in our sensors and in magnetic sensing and in magnets, because often what we find is you might be working with an electrical engineer, that probably took some courses in college around magnetism, but that's generally not what they're experts in. So
Right.
we bring that expertise, and we can help them with the magnet. And we also have a use of a very sophisticated and powerful magnetic simulation tool.
Oh, okay.
Yep. And what we can do is we can take the customer's mechanical environment, basically their CAD files, put it into the simulation environment, place a sensor in that mechanical environment, place a magnet, and then we can simulate the operation of the magnet and the sensor
Very cool.
in their environment to basically validate the design before they ever build anything or prototype anything, which is really powerful.
Okay. And Patrick, can you talk a little bit about what Microchip offers for customers who want to build a sensor node and don't know where to start, or they know where to start, but what kind of tools do we have to make it easier for them?
Yeah, definitely. Well, I mean, first and foremost, we do lots of as many digital things as possible, whether it's, like I said, the videos, tutorials, code examples, or even live streams like we're doing right now, to things that are more like in-person trainings. We also have applications engineers as well that are experts in their own respective fields, whether it's analog, integration or firmware optimization. And then we even have third-party design partners that are experts in their own respective fields. So audio, visual.
Yeah, that's a really cool program.
Yeah, mobile application, cloud application development. Just anything that basically you might not be an expert in yourself, but you have a prototype of, and then but you need to get it to production. These guys are really good at it, and they have most of them have. In fact, I think all of them have like pretty impressive track records from what I've seen.
And other things, easy to use tools. I mean, we showed you the MPLAB code configurator. The goal is, as we integrate more hardware onto these devices, I mean, you can open a data sheet and easily get scared. The code configurator, well, maybe not scared, maybe a little overwhelmed. But if you go into the code configurator, what it does is it kind of gives you a graphical representation of that peripheral. You can set it up using drop-down menus, and it generates some fairly efficient code that you can use as a reference. Now, to locate other resources, we have application notes online. As Patrick mentioned, he actually did a really great video on the low power. I think we talked a little bit about it at the front end of the live stream. Additionally, if you want to go to my computer screen, guys, we have online resources as well. So if you're coming from the AVR aspect of things, we do have the START environment, which is a graphical programming environment. But a really nice feature here is if you go over to the examples section and browse examples, you can literally type in things. Well, you can see here what pops up first is just some low power implementations. You can go by devices. You can get the SAM devices in here as well, any of the AVR devices. If you're looking at maybe a PIC-based implementation, you can go to our MPLAB Express code examples, and that has a similar thing where you can go in and see all sorts of different applications. Some put up by Microchip, some others, like right here, this was put up by a community member, and you can parse through that based on boards and so on. We have a question from the booth?
No, I just want to make a highlight. We're going to be dropping the survey in a couple of seconds. Here, Ross is going to help that out with that. Just make sure you fill that out so that you could win one of the grand prizes for this week, the tickets to the Expo conferences. So, just making a comment on that. So just beware and fill that out. Thank you.
I have a question from one of our YouTube viewers, Akeem. He asks, is Microchip working on embedding low-power LoRa into our chips?
I can't answer that myself, but what I would recommend is, keep an eye on our website. If you're looking with regards to IoT or something, what I would do is just go to microchip.com/IoT. Most of the technologies that we make, if you want to get to that web page quickly without going through the main page, you can just do microchip.com/whatever that technology is, and that'll be your best result there. Keep your eye on press releases, that kind of thing. We do have modules available as well, that if you go in and take a look at our wireless module web page, you should be able to find that. The goal with a lot of these modules is, so you take a device that doesn't have something like LoRa or BLE integrated onto it, and you can add that to your application with minimal overhead. So a lot of these devices will connect over SPI or a UART. If it's a fairly robust software stack that's required, like Wi-Fi, we sell modules with that stack already integrated onto the module, and then that takes the heavy lifting off of the MCU and puts it onto this module. So there's lots of options available. In fact, if you have a customer, my wife and I just recently went and bought a washing machine, and they had some options. They had a washing machine that had Bluetooth connectivity, which I really wasn't interested in, but they had a module that didn't have a washing machine that didn't have Bluetooth connectivity. So for old dudes like me, and you want to expand your application and your customer base, you can have both features but still minimize the design on your platform by using these modules.
Great,
Cool.
thanks. Yeah, one thing I want to bring up, the winners for earlier this week. There's been 10 of them. So check your emails, reply back so we could get in contact with you so we could send out those gifts.
Cool. So one other thing I want to just mention, we have a bunch of boards here on the desk here. These are just a number of the boards that have been created that you may want to take advantage of with regards to things like IoT or wearables. We have, this is a BLE module that we have for PIC and AVR devices. These are boards called Curiosity Nano boards, which basically take fairly high pin count devices and put them on these platforms where you have access to all the pins. They integrate programmer debuggers. This is an 8-bit device. This is a 32-bit SAM device. So, I mean, if you wanted to breadboard a SAM device, here you go. And it integrates the programmer debugger, access to all the pins. If you want to take advantage of some of the microelectronica click boards and use these boards with that, we have this nano baseboard, which allows you to either, you know, put pins on and through hole solder this on, or even surface mount if you want to dedicate this board to this platform. And you have the ability to interconnect with microelectronica clicks, or over here with the Explain Pro modules that you can use with a lot of the AVR products. Last but not least, one thing, just to demonstrate an application that uses this. Kurt, can you hit my monitor again? What I'll do here is I want to show you a collaborative project we had with Rose-Hulman University in Indiana. And what they wanted to do was a cloud-connected classroom. And the way they did that was they had a number of sensor nodes, which were actually made up of our AVR IoT boards, which actually feature Wi-Fi capability. But the sensor node would actually connect with a PIC32 AWS a platform that then communicated, and as I mentioned earlier, did all of the heavy lifting with regards to the web service through, I think it was Amazon on this one. But then they also had the ability to communicate back with other nodes that were actually behaving as actuators. And if you take a look at what they did, basically they put, this is one of the nodes that they had in a closet, and what they would do is they'd heat it up, and when it hit a certain temperature, the fan would come on to cool it. And there's kind of the web service output there. So as you can see, it was a complete solution along with a low power sensor node using an AVR device, and then you had the SAM device, or sorry, the PIC32 device doing a lot of the calculations and processing with the web service. Cool. Gentlemen, I think that's it. Is there anything you wanted to add, or?
I would just, you mentioned the clickboards, and there will be shortly coming out a clickboard that has the Kodo TMR sensors on it.
Cool. And it kind of implements kind of that similar the voltage.
Yeah, it does. Yep, it's got the analog sensor on it and 2 digital sensors with LEDs, so you can visually see response. It's really a cool thing.
So you pick up one of those, you get a couple of these, and look, you're off to the races, man. Any other comments from the booth?
Yeah, we have a couple of comments. Again, check your emails for the winners for this week. We want to make sure you guys reply back so we can get in contact with you. Also, if you want to be the grand prize winner of the Sensor Expos, fill out the survey for today. So fill that out. We'll pick out the winner. You'll get the choice of the expo or another prize if you can't make it. Also, we want to thank everybody that participated this whole week in IoT Week.
Yeah,
So
for
Ross,
sure.
thank you. Tim,
Thanks, Ed.
everybody behind the scenes. Sorry, just checking my notes here.
I have some names, actually.
Oh, perfect.
That went-
Yeah, if you want to go through those names, and I'll come back to me.
Yeah, and I'm sure I'm missing somebody, and I apologize, but this, I don't know if the viewers have watched all week, but I have, and it's been an amazing event. But big thank yous behind the scenes. So we have all the engineers who answered questions on the chat. We have our marketing strategists, Marcy and Nicole, for helping out. Live stream manager, Claudia. Events planner and web page designer, Megan. Graphic designers, Kiet and Jordan. Videographers, Kurt and David, who's in the booth. Mia Lita for helping out with great promotions. I mean, we've got some really good views on this. Anyone else I missed, I apologize. But a big thank you to Rachel. Rachel did an amazing job setting all this up. Kudos, Rachel.
Definitely.
I think that's everybody.
So we
Yes.
just need to add also with the expo tickets that does not include airfare and hotels.
Oh, yep.
That would be on
That's
yourself
good, yep.
to provide that one.
Yeah, and also everybody will be receiving an additional survey, so you can fill that out. Give us some comments. Give us some topic ideas for future live streams. That'd be great. We definitely need that. It gives us some topics that you guys want to see in the chat and on the YouTube videos. We also want to, excuse me. Yep. So the survey that went out on the chat, please fill it out, and then the additional survey that'll be going out. But and then Ross just put out a discount code for the expo. It gives you $100 off, so take advantage of that. If you want to, if you're planning on going to the expo, you could use $100 off towards that. Thank you very much.
We also need to give a
Oh.
shout out to Leah.
Oh, I guess shout out to Leah. Thank you. That's
Cool.
it. Yeah. Thanks, Mark. Thanks,
All right.
Tim, Patrick.
Guys, appreciate your time. Tim, have a safe trip home.
Thank you.
Patrick, I'll see you upstairs.
Right back at you.
Everybody watching, I appreciate your time. I hope you enjoyed it as much as we certainly did. Until next time, Mark McComb, and we'll see you again. Bye.